So what I've decided to do for these chapters is sort of consolidate chapters 11 and 12. I think it makes a little more sense to go back and forth between these chapters. Plus, there's a lot of material that I don't think you need to know quite in the detail that the book has it in. Our primary goal is to teach you what you need to know for carbohydrates, lipids, and amino acid chemistry, that is protein chemistry. And so what I'm doing is I'm, for the most part, paring the chapters down to that material. And then I'm also going to include a little bit of material that I think is also important for you to know that's based just some general organic chemistry stuff about aldehydes, ketones, and carboxylic acids. So let's get started. We're going to start with ketones and aldehydes. Now, when you do the homework, look at the homework in the sections that are listed. So this is listed as chapter 12, right? Sections 1 and 2, and that's what you'll do your homework based on. Because I'm not using PowerPoint, you won't be able to follow my cursor as easy. So what I'll try to do is make sure that I underline or highlight things as I go along. So let's start with aldehydes and ketones. So what is an aldehyde? The functional group that's important for all of these is the carbonyl functional group. And so it looks something like that. It's a double bonded oxygen to a carbon. And the carbonyl can have either alkyl groups on the sides. It could have a hydrogen on one side, and that would make it an aldehyde. Or when we go down to carboxylic acids and its derivatives, we can have another group, functional group on this end over here. So simply though, for carboxylic acid, or for ketones and aldehydes, we have this. So for ketone, we'll go like this. Oh, sorry. We'll draw one here. So this is a ketone. It has 4 carbons, and this would be called 2-butanone. Or you could just call it butanone because it doesn't matter where you put the carbonyl group. It'll always be the number 2 position, either there or there. Okay, so 2-butanone. Now, the way I generate the name is I just take the name of the functional name of the alkane, so it's butane, and then I get rid of the E and I add O and E. So that's the way you'll name all ketones. So for example, we'll do this one. And the way you would name this is you would start with, this is the number 1 carbon, and 2, etc., 3. So the chlorine is on number 4. Now I have 5 carbons here, so this would be a pentanone. So I named the, remember, pentane, and then replace the E with the O and E. And then I just have to put the name together. So it's going to be 4-chloro, 2-pentanone. Now, you can't leave the 2 off in this case because there's actually another compound. For example, it would look like this. I'll do it right underneath. And this would have a different name. It's a different ketone. So this would be 2-chloro, 3-pentanone. Now, because the ketone is on the central carbon, I could have numbered it from either end. And so what I did is I numbered it from the end. That gave the substituent the lowest possible number because the ketone would always have the same number. Now, aldehydes always have to have a hydrogen next to the carbonyl functional group. So let's say this is my aldehyde. I think I'll use a smaller pen and then I could write a little bit smaller. So here's a hydrogen. That's what makes it an aldehyde. You don't need to give the aldehyde a separate number because it's always number 1 provided that there are no other functional groups on there. Now, in terms of naming priority, aldehydes and ketones are higher than priority than alcohols, amines, anything that we've learned in the past. And between aldehydes and ketones, aldehydes are slightly higher or just one step higher in priority than ketones. So we'll go ahead and name this, and I'll go ahead and put this group here. Okay, so this would be, again, 1, 2, 3, 4. So the way we generate the name for the aldehyde is we say, start with the name of the alkane, so it's butane. And then we get rid of the E, and then we add Al. So this would be butanal. And so we have butanal, and on the third carbon, we have what's known as the oxo-functional group. So if you have a carbonyl group in the middle of the chain, and it's an aldehyde, this group, let me get a green pen here. This is the oxo group. And it's on the number 3 carbon. So now this is 3 oxo-butanal. Okay, so that's it really for the nomenclature. Nothing really remarkably different than anything we've done before. Now, this is what's a little bit different. You're going to need to know some of the common nomenclature that's associated with aldehydes and ketones. And to do that, you need to know some new prefixes. And I'm not going to make you memorize all the prefixes, but I'm going to have you go through 5. So this is form, that's 1. Acid, that's 2 carbons. Okay. Propion, that's 3. Butyr, that's 4. Valor is 5, and I'm going to write like that. That's the Roman numeral 5. That's how I remember. And capro, you're just going to have to remember this is for 6. And capro comes from the word Capricorn. Capricorn is a goat, and when goats get wet, they have a distinct smell, which is caproic acid, and that's where it gets its name from. So caproic acid is a carboxylic acid that has 6 carbons in it, which we'll talk about that later. So when you do common nomenclature, so this, for example, now you notice this is an aldehyde. It has hydrogens on both sides. So this is form, and with most common names, you list the number of carbons in the alkyl group, and then you add the name of the functional group after it. So this is formaldehyde. Formaldehyde is related to what we'll look at later, formic acid, which comes from ants, and the formal prefix comes from the term for ants. So acid is 2 carbons. So acetaldehyde would be this. Oops, just 1. And this is an H, and this is a CH3 over here. So this is acetaldehyde. Okay, so now it turns out when you have 1 or 2 carbons, you can only have aldehydes. But if you have 3 carbons, then you could have a ketone. So that ketone would be this. Now, ketone nomenclature, I think I might have said something wrong earlier, although I'm not positive, in the naming of these carbonyl function groups. For the common name for ketones is just generally is generated by looking at the alkyl groups on the ends and saying, for example, this one would be dimethyl ketone. So you don't need to use these. I think what I said is you use these prefixes, form and acid and all those guys, that you use those for ketones and aldehydes, but really you just use them for aldehydes. For ketones, then you just name the alkyl groups on either side and then you name it. Now, this one particular ketone, now remember, this has a carbon in the middle right here, right? And so it's 3 carbons long. As a systematic name, that would be propanone, but the common name for this is acetone. And it's always confusing to students. Why is it acetone? Because this acet and this acet here, number for 2 carbons, are the same actually. And historically, this goes back to the 1600s when the alchemists would make acetone. So this has been around a long time. It's probably in the Middle Ages people started making acetone. And they would take lead acetate or metal acetate salts, and they would heat them up, and this clear liquid would come out, and this black gunk would be left behind. And the clear liquid was acetone. And so that's where they think the name comes from. It's confusing, but it's kind of nice to know the history, like it comes all the way back from the alchemists. I know John Dalton, in looking at his notebooks and some of his papers when I went to England, had special alchemical symbols for acetic acid and things like the common some common compounds had symbols because back in those days they thought they were actually atoms that were acetone until he just discovered and sort of worked with atomic theory and then came up with the idea that acetone was composed of several unique combinations of atoms, basically. Anyways, so that's how you would name aldehydes and ketones using common names, but there's also a prefix system for aldehydes, especially when we're looking at naming them, and that's this. So let's say I take this aldehyde, let's call, and I'll put a chlorine here, and this is a hydrogen over here. So this would be butyryl aldehyde. Oops, sorry, spelled it wrong. And you want to give an indication of where this is. And so in the chain, this is alpha, beta, gamma. And if there's another one, it'd be delta. And so this would be alpha chloro, butyr aldehyde. And then the rest, I can't get it all in there. Oh, sorry, I got a little bit more page left here. Aldehyde, there we go. Sort of like that. So you can use these prefixes, alpha, beta, gamma, delta, epsilon, to indicate positions on the chain. Now, having said that, I just want to be real clear, ketones have an alpha carbon too. And when you're looking at a ketone, let's say like this would be diethyl ketone. This is the alpha carbon. There's 2 of them, one on each side, and this is the beta. If you remember from our discussions of eliminations of alcohols and also of alkyl halides, we had a term called beta elimination. So if I have an alkyl halide like this was the alpha carbon and this was the beta carbon, like that. These are beta carbons on the sides. The reason it's different, because you'll notice the alpha is attached to the chlorine. Here, the alpha is not attached to the oxygen, and that's because it's alpha to the functional group, And the functional group for carbonyl is C double bond O, whereas the functional group for chlorine is just Cl like that. So the functional group contains a carbon, so the carbons adjacent to the functional group are the alphas. The chlorine doesn't have a carbon, so the carbon it's attached to is the alpha. It's the closest one. Okay, so for carboxylic acids, the story is a little bit different on how you name them. There's both systematic and common, and we'll do a little bit of both. And the common names are down below, so we'll do the systematic. So to start with, in the nomenclature of all of these compounds, you start with the name of the parent chain. So if it's 5 carbons, it's pentane, right? So if you're going to do the carboxylic acid, so the carboxylic acid, let's say we're going to do this one. The carboxylic acid functional group has a carbon, a double bonded oxygen, and OH. This would be the number 1 carbon, and it's always at the end. It's higher priority than aldehydes and ketones. And so this would be 1, 2, 3, 4, 5. The number 2 carbon is also the alpha carbon. We would be using that in the common nomenclature. So this is pentane. And again, you get rid of the E, and then you add OIC and the word acid. So I always joke, once students get this, what they say is OIC, because it's pentanoic acid, right? So maybe that'll help you remember it. I don't know. Maybe it won't. Now, if you remember, and then again, the nomenclature rules are the same. So if I add a substituent on the 4 and a substituent on the 2, I would have to list those in alphabetical order. Or if they were the same substituent, I would use the di prefix and list both numbers together. So the rules for the carboxylic acids, the only thing that's different is that carboxylic acid is the highest priority functional group. Everything else falls below it. So if you have a carboxylic acid, it's going to be named as a carboxylic acid and not like a ketone with a carboxylate group on it usually. So anyways, now salts. Okay. What about this? This would be a salt. It's the metal, non-metal ionic compound. And the way you name these is the same rule that you learned in general chemistry. That is 8 and ic go together. So you'll notice these are carboxylate salts and they come from carboxylic acid. So this was pentanone, pentanoic acid. And so the IC will be replaced by ATE. So what we're going to do, it's better than I thought it was. I'll change that in a little bit. This is pentanoate. Now, in the nomenclature of ionic compounds, the metal always goes first. So this becomes sodium pentanoate. Okay, so anhydrides are actually made from carboxylic acids. And so if you take 2 carboxylic acids, let's say these would be propanoic acids, and you heat them up together. So basically you just have propanoic acid. What you can form out of that is you can form the following. So you notice this looks like propanoic acid on this side, and then I'm going to do this. I'm going to draw this in. Sorry. Ooh, sorry. My computer's super slow right now. I'm going to draw this in like this. Now, this maybe doesn't make sense yet, but then you can also have this on the other side. Now, what is missing, right? What's missing is one of the oxygens and one of the hydrogens and another hydrogens. So what you're removing when you do this is H2O. So that's where they get their name. Anhydrides without the water, and anhydrous acids would be, well, it's not really anhydrous acid, but when you remove the water, it becomes an anhydride because you remove water from it. The way these are named is by naming the acids that go to make it and then adding the word anhydride. So this would be propanoic anhydride. If you have different carboxylic acids, so let's say you have ethanoic, propanoic anhydride, what you're going to get is you're going to get this, because it's 2 carbons for ethane, right? So, and then you have an oxygen, and you'll have the other side will have 3 carbons like that. And that's a mixed anhydride. You don't use the word di because in order to have an anhydride, you have to fuse 2 together. So that's kind of understood for propanoic anhydride. But for ethanoic propanoic anhydride, it's fairly clear that you have an ethanoic acid and a propanoic acid. Now, esters get so in part, right? If you know the name of the acid, you can name the anhydride that it would make. So 2 pentanoic acids that got together would just be called pentanoic anhydride. It turns out esters are named from the carboxylate salts. So an anhydride is this kind of structure, and I don't know how that happened. An ester is this kind of structure. Let's see. I will do like this. So for carboxylic acid, what would be on that oxygen would be, or for carboxylates, what would be on that would be a metal ion. For esters, it's another alkyl group. So let's say it's this. So that's an isopropyl group. And the way this gets named is it's named after the carboxylate salt, where this replaces the name of the metal. So what's attached to the oxygen, the single-bonded oxygen, is what we put in the front, just like we put sodium in the front here. So this would be isopropyl. That's the simplest way to do it. And then this is a 3-carbon carboxylic acid. So propanoate, just like that. Okay, so we use the name that we would get from the carboxylate salt, and then we add the name of the alkyl group on the oxygen in front of the name of the carboxylate. The amide functional group looks like this. One's on here. Let me add a BR here like this. Okay, so this would be a N, where the R group and the nitrogen has lone pair on it. The R group could be hydrogen. Now this is also a substituent, and so this becomes N. To name it is similar to locant carboxylic acids, methyl, because it's located on the nitrogen. So let's say I have NH, then CH3. Okay, so amides are very similar. Again, the only thing weird about amides, they're like amines. Remember when we did amines? To name this would be a 1. The locant was N because to indicate that it was on the nitrogen. 5-carbon chain. So that would
summarize
be a
the
systematic
pentane,
nomenclature.
right?
I do expect you to know this. There won't be that many nomenclature
amide.
questions
So we just get rid of the
on
E,
your
just like we did
test
for
when we cover
carboxylic
this
acid, and
material,
we add the
simply
word
because
amide to it.
it's all open
Now,
book
when
and
we're
open resource, and those are things you
placing
can just look up. So there'll probably be fewer, but there will still be one or two
substituents on
multiple
here,
choice.
let me add a BR here like this. Nomenclature.
Okay, so this
type
would be
questions. a 4-bromo. Now this is also a substituent, and so this becomes N as its locant or its position, methyl, because it's located on the nitrogen, and then pentanamide. So we would just tack that on there like that. Okay, so amides are very similar. Again, the only thing weird about amides, they're like amines. Remember when we did amines, if there was an alkyl group on the nitrogen, we gave the locant was N because to indicate that it was on the nitrogen. So that summarizes the systematic nomenclature. I do expect you to know this. There won't be that many nomenclature questions on your test when we cover this material, simply because it's all open book and open resource, and those are things you can just look up. So there'll probably be fewer, but there will still be one or two multiple choice nomenclature type questions. Yeah, I realized as I was about to get ready to start the next section, I forgot one class of compounds, so I'm going to add it right here. And these are the acyl halides. So I'm making a little line here. And the acyl halide. So an acyl halide looks, for example, like this. Instead of having carbons on both sides, one side is a halogen, so it could be like a chlorine. So to name an acyl halide, you take the name of the anion that we have up here. So for example, if this had 5 carbons in it like that, then this would become pentan, and then you get rid of the 8, you remove that, and you add the ending YL, so it becomes pentanoyl. That's one word. There's not supposed to be a big space. And then you name what this is at the end. So this is chloride. That, okay? So those are acyl halides. You could have a functional group on the chain, and following the standard nomenclature rules, you would just give it a substituent number and then add it to the front of the name. And again, if you have more than one of the substituents, you can use the prefixes like di, tri, tetra. And you can also have other substituents, and you just list them in alphabetical order. Okay, so let's look at the common names for these compounds. I'm going to run through these fairly quickly. So for carboxylic acids, we would use these prefixes in the common names, the ones that are shown over here. And then we would change the suffix. So for example, for a 4-carbon chain, like this. If I have a carboxylic acid that looks like this is butanoic acid, but butyric. So we add the IC ending on it, and we say acid. Okay. If I had a chlorine in the second position, that is, if I had, let's do this. I'll do one here like this. I'll do the chlorine there. So the common name would be, this is alpha and beta. So this is beta chloro, and then it's a 5-carbon, and 5 is the valeric, so valeric acid. I don't need the hyphen, sorry. So it's a beta chlorovaleric acid.
So in naming anhydrides, we're going to follow the same format that we did for systematic nomenclature by naming the carboxylic acids that were used to name it, and then adding the word anhydride to the end. So, for example, one of the very common ones is this. We use this in lab quite often. This is known as ethanoic anhydride. That would be the name of it systematically, but then if we were doing the common name, 2 carbons is this acet, so it's acetic acid. We just add IC to the end, just like you do for carboxylic acid. So it's acetic and then the word anhydride. Okay. So common nomenclature is fairly straightforward for anhydrides. So again, in carboxylate salts, all we've done in the common nomenclature is we still keep the stem of the name is what it's called, and then we change the suffix to ATE. So if I had, for example, this, again, this would be in the systematic nomenclature sodium ethanoate, because you put the metal in first. This would actually be called sodium, and it's acetic, so acetate. IC becomes ATE, so acetate. Again, very similar to the systematic nomenclature. We're just using these different stems to indicate the number of carbons. Esters, same thing. If I had an ester that looks like this, again, an ester would have a carbon chain to one side, so I'll just do it like this so it's easier to see. This is an ethyl group, so this would be ethyl. Now, 1, 2, 3, 4 carbons in the chain, so 4 would be butyr, so butyrate. We had ATE. Again, both the carboxylate salt and esters share similarities in they take their name from the carboxylic acid, and then we either add the name of the metal in the front or the name of the alkyl substituent in the front. Amides, similarly, right? If I had this is ethanamide. This would be acetamide. So again, we just use that same stem and then we create a name out of it. And then lastly, if you have the acid chlorides, which I left off. Let's say, or acid halide, so it could be a bromine too. Let me do a bromine. And then it's the acyl halides. Sorry. Put a bromine here. So that's 3 carbon. So that's a bromate or a bromic acid. That's where it's derived from. And then we name it propionyl. There we go. And then bromide. Adding the halogen at the end. Let's do this. Let's do this the same one. Let's do this. That would be acet, and then YL, and then chloride. Okay. So again, it's following the same format as the systematic nomenclature. It's just using these older names for them. The acete, the propion, butyr, valor, and capro. So let's talk a little bit about the structure of the carbonyl functional group that's in the middle of all these different functional groups. So it's sp2 and trigonoplanar. So what does that mean, right? So sp2 means that looks like this. So again, 3 groups, and it's flat, so all these atoms are in the same plane. Now, when you think about when we're talking about nucleophilic substitution reactions or nucleophilic addition reactions, one of the things that we've dealt with so far for the most part is that we're dealing with tetrahedral centers. So this is not tetrahedral, this center. It's flat, and so the result is sterics is not so important when the nucleophile comes in. And these will all be nucleophilic reactions, so a nucleophile will attack at that carbon, okay? Now, that carbon is actually very positively charged, one, because the oxygen is more electronegative than the carbon. Or sorry, carbon. I don't know why I wrote nitrogen. And then also, the other thing that's important to recognize is there are some resonance contributors that also help to make it more positive. So we have this structure that looks like this, and then we can have a resonance contributor that looks like this. So we have a very strong partial positive charge. So when we're looking at a carbonyl, we're thinking of a partial positive on this side and a partial negative on this side. So again, this area is susceptible to nucleophilic attack because of its positive charge. The other thing that's going to happen when you think about the way this structure is that carbon can only take 4 bonds. So when a nucleophile comes in, well, let me do it down here. When the nucleophile comes in, like this, right, then this pair of electrons has to move out of the way. And you'll end up with something that looks like this. And I'm going to call this R so I don't lose track of it. I'll have the oxygen will be bearing a negative charge, and then the nucleophile will be attached. And the nucleophile may or may not have a charge at this point, depending on whether the nucleophile was negative when it came in or positive when it, neutral when it came in. So we end up going from trigonal planar and we're ending up as tetrahedral. So there's a number of different reactions in these 2 chapters, but all of them start off with this first basic step that a nucleophile comes in and goes from being trigonal planar and becoming tetrahedral. Occasionally there's a step before this step where the oxygen gets protonated first, but that's usually the role of a catalyst. But the rate determining step in most of these reactions is the formation of this tetrahedral intermediate. So let's talk generally how these reactions take place. Okay, so we have a nucleophilic attack. We mentioned this before. You have a carbonyl functional group, and in the carbonyl functional group, you have a very positive carbon, and then we form a tetrahedral intermediate. So a nucleophile, we'll call it Y, let's say. We'll call it Y minus, because good nucleophiles, right, negatively charged, comes in and attacks and goes like that. And so what you end up with is you end up with this tetrahedral intermediate where you'll have Y attached to the carbon, you'll have the oxygen with its negative charge, and you'll have, let's say, R1 and R2, 2 different groups, okay, attached to it. Now, if we're talking about carboxylic acids, what ends up happening is that this group can be a leaving group for carboxylic acids. So this group here can be a leaving group for carboxylic acid. So in this tetrahedral intermediate, I have a negative charge, I have my electrons here, this can come in. And if this is a good leaving group, then what ends up happening is you end up getting something that looks like this. And then R1, whichever is the best leaving group, that's what ends up leaving in the reaction. Now, for aldehydes and ketones, what's different is this. When you have a hydrogen for an aldehyde or an alkyl group for a ketone, for example, and these are R groups over here, there is not a good leaving group. These are both bad leaving groups. And I'll just call it LG. The result is when the nucleophile attacks, it stays in its tetrahedral shape. That is, if the nucleophile attacks, then what I'll have is an H here of Y, and my oxygen with its negative charge and another R group. Since I don't have a good leaving group, it's just going to stay like that. For the ketones, you would see the same kind of behavior, but instead of having a hydrogen here, you'd have the CH3 group there. So what ends up happening then is in the first case, that's this case, this ends up being a substitution reaction. Because remember, in substitution, what you have is you have one group being replaced by another group. Okay. Again, this is the intermediate for the reaction over here. So this is the intermediate. And so you have something in the intermediate leaving, and then we call that would be a substitution reaction. So let's go over the reactions of the carboxylic acid derivatives. And these are the substitution reactions. And let me do it like this. I can change my pen so it's actually a blue. Okay. So and let me give you an example of a reaction. So I'm going to have an acyl halide, so like an acetyl chloride, that would be that, and this would be a CH3 here. And then I'm going to use a base, and for my base I'll use let's see, something that's simple, Cn minus. So this is my nucleophile, and then what will happen is this will attack like that, and then I'll end up with, sorry about that, hit the mic, I'll end up with this. And I'll have my electrons on the oxygen. I'll have a Cn and a Cl like this. Now, there's steric strain in this tetrahedral complex. Now I have four things attached. And as a result, it tries to get back to having three things. And the way it does that is when it collapses, one of these two groups has to leave. And the group that leaves is the one that is the weakest base. So if you remember, the weakest base is associated with the strongest acid. So for example, Cn minus is related to HCN. And then Cl minus is going to be related to HCl, like this. Well, HCl is a strong acid, so this is the best leaving group, and so this is the one that leaves. And when the reaction is done, what you're going to end up with is this. Now, we didn't really talk about nitriles, but this is what you would end up with, like that. You'd have this acyl nitrile, and then this group would have substituted for this group. And the group that substitutes, or the group that leaves is the one associated with the strongest acid or is the weakest conjugate base. All right, so looking at it that way then, we have a class of compounds. You notice I changed this page a little bit just because I felt like I really just wanted more room, and I may erase this guy down here too, and then move that to the next page or down further. Let's look at all the carboxylic acid derivatives. So, and then we're going to write it like this, and I'm going to write them in a particular order. So I'll start with acyl halides, and I'll just do this acetyl chloride or ethanoyl chloride, and then the next one I'll write are the anhydrides. So we'll have CH3 and then like this. And this order is a particular order, like I said. And the order is that this is the best leaving group. And then in this reaction, either side could be substituted, but that's the second best leaving group. And then after this, we have esters and carboxylic acids. So the simple the acetic acid would be the 2-carbon carboxylic acid. And then we'll also have, that's ester, sorry. That would be an ester, and then a carboxylic acid. And then amides. Okay, so now what I want to do is look at the acid that's associated with each one of these. So this one would be HCl. This would be HO, and then I don't know if you recognize this. This is just acetic acid written backwards from the way we normally write it. This would be HOCH3. This would be HOH, so water. And this one is methanol. The one to the left of it is methanol. And this would be NH3. And I listed these in order of reactivity, and the reactivity goes entirely with the strength of the acid. So HCl is pKa is less than 0. So it's a very strong acid. Acetic acid, carboxylic acids in general, their pKa's are around 5. And then it turns out that alcohols, pKa's are around 15. And then for water, its pK is also around 15. And then NH3, the pKa is about 35. And so you'll see this progression. These two have about the same reactivity. That is, they're both about the same reaction rate in substitution reactions. And then if you were to look at where Cn minus sits, Cn minus, the pK is around 9. So if we were including this one in the list, sorry, I had the cough, so I turned the mic off. If we're including it in the list, would slot between these two guys in terms of its reactivity. So it falls in between because of its pKa. Okay, so what does this mean? It means if I have, hang on, sorry, draw. Is this the same one? No. Oh, let me fix this. Hang on, I'll pause it and do it. If I have a reaction like this, let's say CH3, let me get my pen back. and then I react that with CH3OH, which is this, then I'll have a spontaneous reaction that produces this. And so I'll have substituted the OCH3 from the methanol for the acetate group that was part of the anhydride. And that'll be a spontaneous reaction. On the other hand, if I try to do this, this will be a no reaction. So I'm just going to write that right from the very beginning. I'll just leave it like that. So if I try to do that, then I can't make it happen. It's not a spontaneous reaction because the spontaneous reaction is the well, let me do it. I better draw it. It makes more sense like this. The spontaneous reaction is for these two to give me that. Okay. So in other words, this reactivity list is telling us the direction in which reactions will be spontaneous. So let me add a page. I'm going to add some more notes in here. Okay, so I've added my page. The thing I wanted to talk about, and it's what I had alluded to in the section that I erased from the original blank notes, which I'll be posting those as well, but this will be the modified notes, is that there's a reaction like ladder that we pay attention to. So we have the chlorides, the acyl halides, are more reactive than the anhydrides. Which are more reactive than the esters. I'll put R here to make it more generic. And also, these are about equal. These would actually be equilibrium to each other. More reactive than this, than carboxylic acids. And then amides are down here. Like that. And it's spontaneous to go down in energy. So this is the highest in energy. And this is the lowest. And just like you expect a ball to roll down a hill, you can expect that anything going down this way is spontaneous, and going the other way is not spontaneous. So there are ways to go back, and we don't really cover those in this class, but there are ways to go back. You can take these, for example, and with energy, and with adding energy, you can take it back up to this point. But through a sequence of reactions. And so what we normally do in these reactions is we make the more reactive compounds, like the acyl halides, and then we react them down to other things. Now, these two are in equilibrium because they're about the same stability going either way. All right, so let's talk a little bit about how you might do some of these reactions in particular. The equilibrium reaction is what I really want to talk about, so we'll talk about this. If you have an ester and you want to make the corresponding carboxylic acid, okay? So you wanted to go this way. This is a bad leaving group. So normally what we do with alcohols, if you remember, when we had reactions of alcohols, what we added was an acid. And we actually do the same thing here. We do something like H2SO4. And then if we're trying to make the carboxylic acid, we can use water. And then what you'll get is you'll get this. And so this is the alcohol, right? and the water got incorporated in the reaction. Water is the solvent, but it's also the nucleophile, so it's a type of solvolysis reaction. And that's what actually, even though this should be equilibrium and have about equal amounts, what makes this reaction really produce a lot of product is you use water um, as the nucleophile or the solvent. You can also do it the other way. That is, if you want to make esters, and this is actually more common, you can start with a corresponding carboxylic acid. Again, this is a bad leaving group. So you can add acid and then the alcohol you want to add to it, and then you'll end up with the substitution that looks like this. And I'm not going to go into the mechanism for this, but it is in the book. And really all you need to know is that you're doing a substitution when you're adding either the acid, and it could be written as H2SO4 or H+, or you probably wouldn't use the HCl, but you could do things like that. And then this is the nucleophile, or for a solvolysis reaction. And remember, solvolysis just means the concentration of the solvent is high. And the solvent is the nucleophile in the reaction, and so its concentration is high. Okay, so one of the things that was on that earlier page is a kind of nucleophile that is an important class of compounds that we need to cover, and those are Grignard reactions. So Grignard, or are also sometimes known as organometallic. So organometallic. Okay. What does that mean? Organometallic just means it has an organic component to it and it has a metal to it. And Grignard are the magnesium organometallic compounds. And so, for example, this would be an example of a Grignard reagent. Now, if you remember your general chemistry, magnesium has a 2+ charge. Bromine has a 1- charge as a bromide ion in ionic compounds. So that means this carbon has a 1- charge associated with it. And what it behaves like is it behaves like this. So it behaves like a carbon nucleophile. And we can use that in reactions with aldehydes and ketones, as well as in reactions with carboxylic acid derivatives. And so let me give you some examples of that and how you would do it, and then tell you when you can't use it, for example. But let's say you took a ketone. Okay, so this will be an example of an addition reaction to a ketone. And I have let's do an aldehyde. Sorry. And then again, I always just draw the one carbon here, but really there could be any number of carbons on that side. And then you have CH3, CH2, and then MgBr, like this. And this has the pair of electrons. What it's going to do is it's going to attach itself like this, and then this will come out, and then you'll end up doing an addition reaction. So you're not really adding this part. What you're going to end up is this. Doesn't matter which side I put the H or the CH2, CH3. I'm not trying to imply any stereochemistry in this. And then you'll have a negative charge up here now. And so normally what happens is this magnesium, which has a positive charge on it, will do this. But this isn't what you normally want as your product. So this is actually the step 1 of the reaction. And then the step 2 is to add H+ to it. And sometimes we'll add hydrochloric acid, for example, but sometimes water works just as well. And so we'll end up protonating it like this. Oops, sorry. Proton H, and then CH2, CH3, and then the hydrogen is still here. And so what we've done is we've added an alcohol functional group, or created an alcohol functional group out of the carbonyl of the original compound, out of this guy here, right? And so I've added this, and so this is an addition reaction. So I can go from a, where's my pen again? There we go. I'm going from a alcohol, or a carbonyl, to an alcohol. Now, if you have a aldehyde, you're going to get a secondary alcohol. It'll look like this. And this, oh, something happened to my word alcohol. I think I left some letters to alcohol. There we go. They're going to end up adding an R group over here, right? This will be R prime MgBr, and then the second step is to add H plus to it somehow. That could even be, like I said, be in the form of water. And so this will be a aldehyde to secondary alcohol. Man, I'm just not putting all my letters down. And then if I have a ketone, same set of conditions, I'll get a tertiary alcohol, because I'll have an R here and an R here. So those don't change. And I'm just doing an addition. So I'll have an OH and I'll have an R prime that I've added. So this becomes a tertiary alcohol. So ketones, and this is a tertiary alcohol. Okay, so that's a straight up addition reaction with a Grignard reagent. Now, if you think about it, the reason it's not a substitution is, for it to be a substitution, H minus would have to leave, and H minus is a very strong base. So that guy never leaves just because he can't leave. If you were to look at this, the ketone, that would have to leave, and R minus would be a really strong base, so it's a bad leaving group. So there's nothing there that can actually leave. Now, if I do it like this, though, let's say I take, and this will be for carboxylic acid derivatives. So that's carboxylic acids, but acyl halides and things like that. So I take an acyl halide like this, and I add, let's say, R MgBr. What you'll end up with is, again, you would think that you would get a substitution reaction, but what you end up getting is this. You end up adding R twice. Okay, so this is actually two equivalents, or two of these R MgBrs for every acetyl chloride that we have there. So why is that, right? So in the first addition, when you do the first one, you're going to end up with this. This is the intermediate. So that's my intermediate, and this is a good leaving group. And so what ends up happening is the tetrahedral intermediate has that strain that we talked about. It's going to collapse, steric strain, because the groups are all clustered together now. It's going to kick that chlorine off, and what you're going to end up with is a ketone. And this is not something normally that's stoppable. It happens very fast, this second step. So I end up with that, and this is a ketone now. So this was an acyl halide, right? After the first Grignard reagent adds, I get a ketone. And then a second one adds, using the same mechanism that I showed basically up here. Second one adds, and I end up getting a tertiary alcohol. So this is a difference in how these two might react. Now the first step is essentially the same. I do an addition, but now we get an elimination because I have a good leaving group. So I'm going to end up with R and R, and so this is my tertiary alcohol, like that. And you add 2 of the Grignard reagents. Before I go on and talk about properties of these types of compounds, I really want to quickly list for you what you need to know out of all this, because I know it might seem a little bit overwhelming. One, you don't have to have the mechanisms for this section memorized, so don't worry about mechanisms. Now, it's important that you should be able to follow along a mechanism, but you don't have to have it memorized. You should be able to predict what the products of a reaction will be just based on the type of carbonyl compound you're starting with and what the reagent looks like. So the thing you do want to worry about is this, that ketones and aldehydes, we get addition reactions. And so you should be able to recognize, for example, if I have, let's say I have CH2CH, let's see, how do I want to do this? Let's do one like this. I'll do it as a line drawing. So let's say I give you this as one of the reagents. You should be able to recognize that the nucleophile out of that is going to be doing the addition would be that. And that's what you're going to be adding on there. Or if it's like this, then the thing that you're going to be adding is this. Because you're going to get rid of the hydrogen, and then you're going to add the oxygen or the carbon that was attached to that hydrogen. And the point of attachment is here. I'll draw that in a different color, is here, like this. Okay, so you should be able to predict the products just by knowing that you get addition reactions. That's what the addition is going to look like. Okay, so also beyond that, you can also have substitution reactions. Now there's more reactions than this, and we're going to cover them because they're important for understanding how sugars react. But for now, we're going to have substitution reactions. And in the substitution reaction, it's the same type of prediction. Addition reactions are for aldehydes and ketones. Oh, sorry. And then for carboxylic acid derivatives, okay, so that's not the aldehydes and ketones, but it's all the other compounds we talked about. We primarily get substitution. And the substitution still follows along this kind of logic. You could have all that in here, okay? That you should be able to recognize the nucleophile from the structure of the compound you're given. And the other thing you have to have in consideration is you have to know the reactivity ladder. Now, you know these are open note type tests. So the important thing about open note type tests and the way they have value is they force you to prepare for the kinds of questions that you're expected to get. And so you should have this kind of material or this kind of material handy on a separate sheet of paper so that you can reference it quickly. And that really does mean, for the most part, rewriting those things in a way that's quickly accessible. And that's where the value of a take-home, time to take home or online test is. it's not in the pure memorization, but it's in your ability to organize and put this information together. Okay. All right. So let's talk a little bit about properties. Properties and where we find these things, because I think that's kind of interesting too. Properties are basically not very remarkable. In general, they have weaker intermolecular forces. Now, the exceptions are carboxylic acids and amides. Weaker intermolecular forces, so they have lower boiling points than alcohols. Okay, so for example, this is polar, right? So all of these types of compounds have, but alcohols like ROH has hydrogen bonding. So as long as the molecular weight is around the same, the alcohol will have the higher boiling point because of the hydrogen bonds. And that's one of the reasons why carboxylic acids and amides have higher boiling points, is they can hydrogen bond. But they also do something else that's interesting. So remember, to hydrogen bond, you have to have a group that looks like that on it with an oxygen and a hydrogen, or for amides, you have something that looks like this, right? And so this is the NH. NH can also hydrogen bond. But what makes hang on, I got a dog. Yeah, so one of the difficulties of teaching at home is all the constant interruptions. I've been up about 20 times during this lecture. So there's a little disjointed. It always is that way. Now, the other thing that's important to understand about amides and carboxylic acids, and we see this kind of behavior actually in DNA, is we see sort of like reciprocal hydrogen bonding. So if I take, let's say, a carboxylic acid like this, I can draw another one like this, and they fit perfectly together. And so there can be hydrogen bonding here and hydrogen bonding here. This can be an R group, this can be an R group. And they sort of form this ring. Well, they don't sort of, they do form a ring. And they essentially dimerize in solution, or when they're in pure, as a pure substance. And so what ends up happening is it effectively increases their molecular weight and causes them sort of to bond together very strongly. And so carboxylic acids and amides, the thing that's remarkable about them is that for their weight, their boiling points and melting points tend to be about twice that of other compounds of similar molecular weight. So instead of, let's say, boiling at 60 degrees, it'll boil like at 200 degrees, that kind of thing. Okay. Now the other thing to know is that carboxylates salts, for example, like sodium acetate, have high melting points simply for the same reason that all ionic compounds do, is because they have these positive and negative charges, and so those ionic interactions are relatively strong. All right. Water solubility, I'm not going to go a lot into this. I think people make way too much out of this. But generally speaking, more than 4 carbons is not very soluble in water, and 4 or fewer carbons tends to be relatively soluble in water. I don't think you need to know any examples of that, but if you're dealing with esters or anything of high molecular weight, they typically are not soluble in water, but they'll be soluble in organic solvents like hexane or other kinds of organic-y solvents. Okay, where do we find these in nature? Well, carboxylic acids we see a lot. We see them as part of like lactic acid or pyruvic acid. These are terms you're probably familiar with being in a Chem 8 class. These are organic acids that we find in metabolism, but these are types of carboxylic acids. If you need the structures, you can look those up. And in the chapter, they're actually listed in your chapter. Amino acids as well are a type of carboxylic acid. They're just a carboxylic acid, for example, with an amine functional group on the alpha carbon, and then there's an R group that's down here, which makes all the carboxylic acids different. We deal with esters. Esters, for example, like this ester, I'll just draw one for you, is a fruity smell. This is known as isopentyl acetate. Now this is isopentyl because there's 1, 2, 3, 4, 5, right? 5 carbons, and this is the acetate portion. So isopentyl acetate smells like bananas. But you can have it smell like pineapple by changing this group or changing this group, changing the carboxylate group. You can change the scent or the sort of the way the odor presents itself. Amides are found in proteins and some of the protein structures like glutamine. I'm not going to spend time drawing all these. Again, you can look at them in your book. But also we find them in peptide bonds, and we'll be talking about these later. Peptide bond really is just an amide in polymer form. So you have this, and then you'll have R group, and then you'll have this, and an O, and then this will continue on. But this is, a polypeptide. This is the amide that you find that links proteins together. And then we see a lot of amides in pharmaceuticals. So like acetaminophen and penicillins are examples of amides. And again, I'm pretty sure those probably are in your book. Ketones and aldehydes are, well, some of them can be pretty nasty, but a lot of the sort of sweeter smells we associate with ketones, so like vanilla or spearmint, but also some that aren't so good, like caraway. Camphor, it has kind of a sweet smell, but it's kind of overpowering. And then cinnamaldehyde is what we find in cinnamon. And also the bitter almond taste is also an aldehyde. So those are the kinds of places we tend to find these things in nature. Again, if you need to see more of these things, I recommend that you go to your book and take a look at some of those images. All right, so now what we're going to do is we're going to spend a little bit of time just discussing aldehydes and ketones and how some of the reactions that they have that are different than the carboxylic acid derivatives. There are a couple of reaction types that are important to go over for what we'll be covering in the next few chapters. This first one is a reduction reaction, is what we call it. And it involves a hydrogen nucleophile. And so the reagents for this kind of reaction typically look like this. Sodium and then borohydride, so BH4, or lithium and then aluminum hydride, which looks like this. Now, if you recognize boron and aluminum are both group 3, and they're the exceptions to the octet rule when you draw a Lewis structure. So when you draw a Lewis structure for boron, you can draw it like this, and that is an acceptable Lewis structure, even though the boron only has 3 pairs of electrons on it, so 6 electrons in its outer shell. Now, because of that, boron can actually pick up a 4th hydrogen, and that's actually what sodium borohydride is. It's this. It's a boron in the middle and hydrogens all the way around. And lithium aluminum hydride is similar in its structure. Now, when you pick up the hydrogen and its electrons, it'll have a negative charge, and so that's why we write a sodium with it all the time, because that provides the positive counter charge for that negative charge on the boron like this. Lithium aluminum hydride is done the same way, where the sodium is replaced by the lithium, but the aluminum's in the center, and it also has a negative formal charge on it. The way these reagents work is usually it's a 2-part reaction. So you can take, for example, and let me call this reagent A, this reagent B. Okay, they both do the same thing, but they have different reactivities, so we use them differently in different situations. So let's say we take a ketone like this, and then we use reagent A or B. What you'll end up with is you'll end up with this, an alcohol. Now, it starts off as an O-, and then we add H plus to it, similar to what we had done before earlier in the lecture with another reaction, and that gives us the protonated form like this. Now, the way this reaction works is the hydride behaves, sort of the sodium borohydride. Well, the borohydride reacts as if it was H minus like this. So the H minus attacks here. Those electrons go back up. So now what I have is this, and then the hydrogen is added to that carbon, and then we add a hydrogen through an acid-base reaction by protonating. So a lot of times H plus is HCl or some other acid used to protonate it. Sometimes it can be water, but oftentimes the salt that forms is not very soluble in water, and so it's hard to break that part of it off. So that's what you do with sort of aldehydes and ketones. Now, if you have other carboxylic acid derivatives, for example, you have an ester like this, then it's better to stick. These tend to be less reactive. So the carboxylic acid derivatives are less reactive than, well, not all of them, I said, but I'll specify which ones are less reactive than aldehydes and ketones. And so we tend to use lithium aluminum hydride because this one is more reactive than sodium borohydride, and that has to do with the electronegativity of aluminum being a little bit lower than that. Let's see, is it lower? Yeah, it's a little bit lower than that of boron, and as a result, there's more negative charge on the hydrogen, and that allows it to transfer more efficiently, I guess, or more strongly. So for carboxylic acid derivatives, sort of the esters, carboxylic acids, and amides, we can do this reaction, and we would end up with, so this is using B, we'll end up with this. And it actually gets rid of one of the oxygens entirely and replaces it with two hydrogens like this. So we get a reduction, complete reduction of the carbonyl functional group to an alcohol, even though it had the two oxygens on it. If you take an amine, or sorry, an amide, you end up with an amine. Like this, okay? So those are some of the hydrogen nucleophile reactions. There's also oxygen nucleophiles, which are important in sugar chemistry, and that involves the formation of something we call hemiacetals, which is half an acetal, and then there's acetals, and I'll show you what that means in a second. So when you have, let's say, a ketone, and you react it, put it in water, this could be either acid or base catalyzed. So there's two ways to do this. What you can do is you can form this. Now this is not an acetal or hemiacetal. This is just a hydrate. It's the hydrated form of the ketone. Okay, and so adding acid or base works to make it faster, but this would naturally form in solution. Now, where the other oxygen comes from is actually the water, or if you have sodium hydroxide, for example, if you're using NaOH or something to give you the OH minus, then that'll be your nucleophile, because that's a better nucleophile because of its negative charge. But this occurs in both acidic and basic conditions. So if you take the same reaction, and instead of using water, you use, let's say, acid and let's say methanol, what you'll end up with is potentially two different products. One product is, and so again, there's no water in this part. You end up with one product that looks like this, and then the next product looks like this. I'm sorry. And then the next possible product looks like this. And what you've done is, instead of replacing, let me just draw it and then I'll talk, like that. So you end up with two OCH3s, so methoxy groups on here. So when you looked back here, right, you only need to, since you're adding OH, you only need to add one. But here you're actually adding two, and in fact what you're doing in this second step is you're removing H2O, like this. And the H2O is coming from this here. So this is what's giving me my H2O. The acid provides a proton. It's actually a catalytic reaction, but the acid, in a sense, provides the proton to help that come off. It's an acid catalyst for the reaction. So you don't need to know the mechanisms. I'll draw those at the bottom here in a second. You don't need to know the mechanisms for these ones. But this is a hemiacetal, and this is an acetal. And again, we see this kind of chemistry in sugar all the time. Acetals are formed all the time in sugar chemistry, as are hemiacetals. Where you see them the most, and you may or may not be familiar with this kind of drawing. You'll see a structure that looks like this in biology a lot. And then there'll be other things on the rest of the ring. But this is actually a hemiacetal. The way you recognize a hemiacetal is that it has a carbon, oxygen, carbon linkage. Let me do the middle one in green. Maybe that might make it easier. So I have a carbon, oxygen, carbon linkage that is on a carbon with an OH group. So here's my carbon, and here's another carbon, and then here's my oxygen that is in the middle. And then on this carbon, right, I have an OH group. So I have all the components of the hemiacetal. Okay, see if there's anything else. I think that's it. In sugars, when they link, the way they link is they link together using an acetal bond. Okay, but hemiacetals, when you see like pictures of glucose and fructose in solution, that's typically what you're seeing, is a hemiacetal. Okay, the mechanism for that is a little bit tricky, but it's not hard to understand. So what I'd like to do is go to the bottom here and draw that. But like I said, it's not absolutely important that you know the mechanisms, but it does help you understand where these things come from. Now, it can happen on aldehydes and ketones. Aldehydes actually happens a little bit faster because when you go to the tetrahedral intermediate, the hydrogen doesn't take as much space, and so the reaction can go a little bit faster. So the first step in these reactions, and so the components are this. You have, sorry, I don't know why I drew a flat line at the end of the line. Doing a call out is what that's called. You have H plus, and then we're going to do ROH. And then this is the first step in the mechanism. But aldehydes or ketones, it'll happen the same way. Now, the purpose of protonating the oxygen is to speed up the reaction. The reaction is actually kind of slow without the acid catalyst. Not just kind of slow, it is slow. And so the next step is the alcohol comes in and attacks. And the positive charge on the oxygen makes it easier for these electrons to be pulled up to the oxygen. So that's why it works as a catalyst. So then you're going to end up with something that looks like this. So an alcohol, right? So that's the alcohol part of the hemiacetal. And then you're going to have, I'm going to draw this over here, even though I came in from the bottom. You're going to have this O, and then an H, and an R, and this will have a positive formal charge on it. And then the last step is whatever gave the H was an acid with its conjugate base. That's going to come back in and kick this thing back off, and you'll end up with this. And again, the components are carbon to carbon, and then the oxygen on either side of that other carbon, like that. So there's your hemiacetal. So that's how that mechanism works. Now, to form an acetal, what you need to do is remove water from this. And so it turns out, starting with your hemiacetal, you can continue on and remove the water. And this is the tricky part of the mechanism, or the trickiest part, I should say. So it still involves the acid. And remember, we have to get rid of a water in this. There's going to be H2O down here somewhere. So this is, and the water comes from this oxygen. I think I said that before. It comes from this oxygen here. And so this guy is going to pick up the proton, and then you're going to form this structure. And then what happens is the water gets ejected in this step. So that gives me a structure that looks like this. And this is not stable, this is intermediate. The oxygen needs to give up a charge. And so, let me get rid of this guy over here. There we go, make some more room. Another molecule of the alcohol, so ROH, comes in as in a nucleophilic attack. And then this has to give up the pair of electrons. And this is almost to my, and I'm going to say minus H plus. I'm going to cheat here. We're going to go like this, and then we're going to have OR down here, and we'll have OR up here. And here's the acetal. If you look at the structure of an acetal all the way up here, it's an, it's a carbon, right, and a carbon, and a carbon separated by oxygens like this. Right? And then if I go down to here, what you'll see is I have a carbon and a carbon, and R, remember R is the alkyl group, and a carbon, and they're separated by oxygens here. So that's the acetal. So that's the mechanism for the formation of the acetal. And like I said, you don't need to have this memorized, but it's important you kind of understand how it happens, so that you're not confused about where the different oxygens are coming from. It does help you to remember like what the products are going to look like and what the reaction requirements are. That is, you need an acid catalyst. Now, nitrogens can also act as nucleophiles, but an interesting thing happens when a nitrogen acts as a nucleophile. So if I have, let's say this, ketone or aldehyde. Again, aldehydes are more reactive than ketones, so I'll just put an aldehyde here. And you react this with ammonia. With H plus in trace amounts. You can't have a lot, but you have a small amount of acid present, because you remember that ammonia is a base. So if you don't have any acid present at all, and you add the ammonia, the pH will be too high. But what you'll form is a compound that looks like this. And this is known as an imine. And the thing that comes off with it is water. And I'll address the water in a little bit. Even in the formation of this hemiacetal and the acetal, we talked about the removal of water at some point. And if you remember right, in the formation of the acetal, right, I formed the hemiacetal first. When you look at the mechanism that's down here, you form the acetal that's here. My pointer here. Form the acetal here, and then in this step, this next step, I protonate the oxygen of the hemiacetal, and then the oxygen that's present on that carbon kicks the water off in the next step. Okay, so in this reaction, what happens is the nitrogen is a better base than an oxygen is because it has a lower electronegativity, and so it has this lone pair like this, right? So what ends up happening is in this reaction overall is rather than needing to bring in a second nucleophile, the nitrogen is able to kick the oxygen off all by itself and do that. Now, if you have a ketone or an aldehyde, so I'll draw a ketone. You can also, so this is what happens when you have an aldehyde, right? And or ketone with a ammonia or primary amine. So if you were to do this with a primary amine, what you would end up with is, let's say your amine is R and then NH2 like that. That would be a primary amine. You would end up with this. Now, if you have a secondary amine, then what you end up with is this. Oh, let's do it like this here. And I'm going to do a ketone on this one. So what's a secondary amine look like? Secondary amine would be something like this. Has two carbons attached to it. It'll also have a hydrogen and a lone pair. And the lone pair is important because that's the nucleophilic atom, right? So what you end up with is you end up doing this. Oops, sorry, not an oxygen. You have the nitrogen up here, and my bad. Carried away. And like this. And this is known as an N-amine. Oops, screen shifted. Oop, do that again. N-amine. Because it has an ene, like an alkene, and it has the nitrogen for the amine. Okay, and again, it still has this lone pair of electrons on it. And so this is a little bit more complicated, this mechanism. I'm not gonna go over it, but you need to know that you can form an imine from primary or secondary, or sorry, ammonia or primary, and then you can form the N-amine from the secondary. That basically covers what you need to know for this chapter. I know there's quite a few new types of reactions. There's a lot of this sort of factoidal information in the middle. I won't ask you much of the factoidal stuff in the middle. That's just sort of to give you a reference of why we're learning all this. And then you do need to go back through and you need to understand this whole page here about relative reactivity and how we can have spontaneous reactions, and understand that we have two types of reactions. We have substitution type reactions, so for example, or addition type reactions, like that we have for here with this ketone. This is an addition reaction right here. And then we also have substitution reactions that are like this. These end up being substitution reactions. If you have questions, I know this is a little bit different style of a lecture. If you have questions or comments, please let me know by email. So, thanks.